You know, when you look at a modern car, what's really going on under the hood? Or maybe I should say under the skin. It's not just an engine and some wheels anymore, not by a long shot. It's a full-on, high-speed network, a digital nervous system on wheels. And today, we're going to map it out.
Okay, let's get right into it. If you really want to understand how your car works, everything from the anti-lock brakes to that fancy infotainment screen, you first have to understand how all its different electronic brains, its control units, actually talk to each other. Welcome to the world of in-vehicle networks.
And look, to guide us through this ridiculously complex digital landscape, we're using what is basically the Bible on the subject, Communication Systems in the Automobile by Matthias Rausch. So think of this book as our roadmap. For this explainer, we're going to navigate the big ideas, introducing you to the core concepts of LIN, CAN, FlexRay, and Automotive Ethernet. We're setting the stage for how this whole ecosystem works.
So here's the game plan. We'll start with the big picture, the car's digital nerves. Then we'll get introduced to each of the key players on the team, the super efficient LIN, the toughest nails CAN, the incredibly precise FlexRay, and the lightning-fast Automotive Ethernet. Then we'll wrap it all up by seeing how they're all going to work together on the road ahead.
Right, so you might be asking, why not just one single network for everything? Well, think about it. The system that controls your power windows has totally different needs than the one that fires your airbags, right? One just needs to be cheap and simple, but the other has to be unbelievably fast and completely fail-proof. That's why cars use a bunch of specialized networks, with each one being the perfect tool for a very specific job. So let's start with our first system, LIN. This network was really born out of a super practical need. Back in the late 90s, as cars got way more complex, engineers realized that using the main, heavy-duty network for simple stuff like mirror controls was just, well, it was overkill. They needed a cheaper, much simpler alternative.
And that is exactly what LIN, or Local Interconnect Network, is. It's not trying to replace the big, powerful systems like CAN, not at all. It's designed to work right alongside them, handling all the less critical tasks in the most cost-effective way possible.
So how does LIN keep the costs so low? Well, its secret is this master-slave design. You have one master controller that basically directs traffic for all the other little nodes, the slaves. It tells them exactly when to talk. This simple, scheduled approach means its behavior is totally predictable, and you can often just run on existing hardware. It's the perfect, cheap solution for comfort features like your seats or the rain sensors.
Okay, so now let's move from that specialist to the real all-around workhorse of the car, CAN. This is without a doubt the most common and probably most important communication network you'll find in a car today.
Yeah, this one's been around for a while. Developed by Bosch way back in the 1980s, the Controller Area Network, or CAN, just hit the absolute sweet spot. It's affordable, it's incredibly robust against electrical interference, and it's pretty simple to implement. All of that is why it became the undisputed industry standard for decades.
Now, the big difference with CAN is its whole philosophy. Unlike LIN's super rigid schedule, CAN is event-driven. You can think of it like a group chat. Nodes only speak up when they actually have something important to share. Every node is equal, there's no single boss, and its real killer feature, amazing error detection. If any node on the network hears a message that sounds even a little bit garbled, it immediately throws up a red flag, forcing the message to be sent again. This makes sure that everything from the engine to the brakes has absolutely perfect data to work with.
And this really sums it all up, doesn't it? LIN is like a top-down, scheduled conference call for simple, low-cost tasks. CAN, on the other hand, is a peer-to-peer, speak-when-you-need-to network for robust, critical control. A car absolutely needs both of these communication styles to work efficiently. But you know, as cars kept evolving, even the mighty CAN wasn't enough. For these new, really advanced safety systems, I'm talking about things like steer-by-wire or active suspension, engineers needed something more. They needed a guarantee, not just that a message would arrive, but precisely when it would arrive, down to the microsecond.
And this is where FlexRay comes storming in. It's what's called a time-triggered system. If CAN is a conversation where you speak when you need to, FlexRay is a perfectly synchronized orchestra. Every single device has a precise, pre-assigned time slot to communicate. This gives you that guaranteed, predictable timing that is absolutely non-negotiable for safety-critical functions.
And the features here are just incredible. It runs at speeds up to 10 megabits per second, way faster than standard CAN. It can use 2 separate channels for full redundancy. That means if one wire gets cut, the other one takes over instantly, so your steer-by-wire system never ever misses a beat. All the nodes are synchronized to a global clock with microsecond accuracy. What do you get? A system so tough it can handle any single point of failure without interrupting communication. You know, FlexRay was a massive undertaking. It was developed over an entire decade by a consortium of the industry's heavy hitters, think BMW and Daimler, who knew they needed this next-level capability. Its whole journey from just a concept in the year 2000 to a full-blown international standard in 2013 just shows you how mature and essential this tech has become. Okay, so we've got networks for cost, for general control, and for time-critical safety. What's left? Data. Just massive, overwhelming amounts of data. And for that, we have to turn to the future, which is automotive Ethernet. Now hold on, this is not the same Ethernet cable you plug into your router at home. That standard Ethernet was way too expensive and honestly just not tough enough for the harsh environment of a car. So starting around 2007, a specialized version was developed to be lightweight, super robust, and capable of handling the enormous data speeds that modern features demand. And the speeds here are just staggering. We're talking 100 or even 1,000 megabits per second. That's a quantum leap over the other systems. It can send and receive data at the same time over a single, lightweight pair of wires. This is the only tech that can handle the absolute fire hose of data coming from high-res displays, multiple cameras, and advanced sensors. It's what makes things like over-the-air software updates even possible, and it is absolutely essential for the kind of data processing you need for autonomous driving.
All right, so we've met the whole team. But the real magic isn't in any single one of these systems. No, the magic is in how they all work together.
So just think of it like this. A car has a specialized communication toolkit. You've got LIN handling the simple comfort jobs because it's so low cost. You've got CAN as the reliable choice for general engine and chassis control. FlexRay provides that time-triggered precision for the most critical safety systems. And finally, Automotive Ethernet serves as the high-speed data backbone that connects everything.
So here is the crucial takeaway. A modern car is a network of networks. It's all organized into different domains, like the powertrain, the chassis, the infotainment system, and each domain uses the absolute best communication tool for its specific needs. They don't compete with each other. They collaborate to form the complete, functioning digital nervous system of the vehicle. And that kind of brings us to a final thought. We are right on the edge of cars becoming true data centers on wheels. So the real question isn't just how these networks work today, but how are they going to have to evolve together, getting even faster, more secure, and way more intelligent to finally deliver on that promise of full autonomy? What comes next? Well, that's a story that's still being written.